Hello, this is Emre Erdem. Today I'm going to go over the facial recognition case study, and yeah, I will go over the detailed report. So the facial recognition problem is basically identifying images and classifying them into the people, so identifying who this image belongs to. And I did some research, this research, and it showed that there are a few different models that were quite successful. The first successful model was probably the eigenfaces method. It used a more traditional machine learning algorithm with a combination of PCA and SVM. Um, and then the second one was the custom convolutional CNN architecture, basically using a convolutional neural network architecture to classify images into the people. Then there were some good attempts by in 2015, and these were achieved through VGG16 architecture and then the resonant 50 architecture. So I tried all of these, and I will share my results with you. So the data set I used is the publicly available facial images from the University of Massachusetts called Labeled Faces in the Wild. And sklearn has a feature that makes it very easy to download and load the data set. And in order to build the model, I first loaded the facial images of the people who have at least 60 images, so that I have enough data for each person. And this basically comprised to be about 1,300 images of 8 subjects, and the images were already pre-processed, so I didn't need to detect the face or crop it, so that was already done. You can see the libraries that I have used, so mostly sklearn libraries for the first eigenfaces method. And the data set, as you can see, is quite easy to load. So this is done by using fetch LFV people method here, using the sklearn data sets, which will download the data. And then what I used was basically just some exploratory analysis of how many images there are, how many features. So there are about 2,900 pixels basically in each image, and there are 8 classes, meaning there are 8 people, and you can see basically how the images look like, and for this purpose the images do not have any color, but the faces are, as you can see, they're of famous people like Colin Powell and Josh Bush, and yeah. So and then we go towards building a model. So the first thing I do is, of course, split the data into training and test sets. And I basically load them into 4 different groups: X train, X test, and then Y train and Y test basically has the identities of the people. I use a 25% test size, um, and um, basically I then built the PC algorithm. So I tried a couple of different dimensions, but 200 seemed to be quite good. So you can see the explained variance here and the number of components, and basically 200 basically captures almost all of the data, the explained variance in the data. Um, and if I do an inverse transformation to visualize the data with the 200 dimensions compared to the original images you can see here, yeah, the images are basically a lot smaller in size, so going from 2900 to 200, so it's about a 10 fold reduction in data, but you can still pretty much detect who these people are, even with the projected images. Then what I use is basically an SVM method using a grid search, basically optimizing for C and gamma, and then building a classification model that predicts yeah, who the image belongs to. So I did this to basically have a baseline model so that, later I can compare this with the CNN or deep learning approaches. So the traditional machine learning approach basically achieved an 81% average F1 score. I also basically showed here the precision and recall and F1 score for each images. So, I know which people are predicted better than the others. And the average F1 score is basically, I think it's a good measure of, precision and recall. And here you can see the best people. The best person to predict was Tony Blair, basically, followed by Hugo Chavez and Bush, and then Colin Powell as well. And yeah, and you can also here see the basically confusion metrics as well. You can see, pretty good accuracy here. And then I just plotted basically the predicted for each image, basically who the model predicts and what is the true value. So here you can see that, it was predicted Schroeder and it was really Schroeder. And then, so this is for a qualitative assessment. And this person was basically predicted Blair, but it was actually Bush. So yeah, so I think, the model performs well, but it could definitely be better. So what I did was, on the next stage, I built a custom CNN model, and I used Keras for that, using TensorFlow backend. This time though, I loaded the image again because for CNNs, for the traditional machine learning, I had to flatten the image basically, so that each image is basically one row. All these pixels are basically concatenated. But here with the CNN, I don't need to do that. So you can see we have 1,300 images, and by the height is 62, and then 47 is the length, and then 1 is basically it means it's black and white, and there's one color dimension. And then I basically do the splitting, training and test split again. I classify Y train and Y test as categorical, and then I also divide it by the color dimension for X train and X test, so it's easier to process by the neural network. The model, I tried a couple of different models, but basically what I ended up was having basically starting with, so I had 4 convolutional neural networks, layers. So the first one is, a convolutional 2D layer, followed by a max pooling layer to basically reduce the dimensionality, and then followed by again the same kind of convolutional layer with more nodes, and then another convolutional layer followed by a max pooling, and then one more. So basically 4 convolutional layers followed by a max pooling layer. And then I flatten a flattening operation, and then I use a dense layer of 500 nodes, and then followed by a dense layer of 8 nodes. So this is to classify the images into 8 different people. And you can see basically the summary of the model in more detail. For the model, I use categorical cross entropy. So since this is a multi-class problem, I use Erdem optimizer, and I basically portrait accuracy as the metric. I started with 10 epochs to start with, and then a batch size of 128, and then I fit the model and to validate on the X test as well. And you can see here, the model basically performed a 43% accuracy, which wasn't great. So what I did was, it was clearly getting stuck in a local minima. So what I did was, I tried to tune the hyperparameters and also add a L2 linearization at the end of the dense layer. to optimize the neural network, and this time it, even in the first epoch it started with the 54% accuracy, and then basically the training set test set accuracy was about 99%. And for the test set, you can see here the more detailed results. So the F1 average score happened to be 86%, and the confusion matrix is quite better than the more traditional method. So after, I think this was a quite good model, but I also wanted to try different, more deeper architectures as well. So the first one I tried, as we also saw in the class, was VGG16, and this time I also loaded the data with 3 color dimensions as well, as this is how the VGG16 expects the data to be. And then basically I use, as you can see, as the conv-based VGG16 architecture, followed by the dense 500 dense layer with 500 nodes, and then again ending with 8 nodes. I also used stochastic gradient descent, and tried different learning rates as well. And I tried quite a few different hyperparameters. Let me show you. So here, these are all the hyperparameter tunings I tried. I tried different bait sizes. I tried different altitude regularizer values, different learning rates, epochs, and I also tried using class weights, non or balanced. But however, basically, I always ended up, getting stuck in a local minima with this architecture. And it was basically, the model was always predicting everyone to be George Bush, since it was the biggest, it was the largest in the data set. Even though I tried, adding the class weights as well and regularization parameters, I haven't ended up with a better performing model. I also tried the ResNet 50, which is supposedly a better performs better in image recognition tasks, according to the article I have read. I also used the same kind of approach. I used all these different hyperparameter tunings, and these different values. So I didn't, show every single parameter result here, but basically this one also predicting mostly George Bush. Also, it predicted a little bit more others as well, but it seemed to get again stuck in a local minima. So the VGG16 and ResNet models didn't really perform very well. It didn't perform better than the custom model I have. I think, so I also shared why I think that's the case. I think the data I have is quite small, 1300 images. So it is perhaps why a deeper architecture is not really needed. And to achieve a good performance, probably more data is required. Possibly data augmentation can be used. And for example, for ImageNet, the VGG16 and ResNet models were trained for 1000 images for each object. So here we have only 60 to 200 images for each identity. So that could be the avenue to take to achieve a better performance with these models. So for these, just to conclude, the CNN model achieved, average of 86%, which is quite good, and it performed better than the more traditional approach of eigenfaces, which achieved an 81%. More, if I had more time and research, I could probably work on the VGG16 and ResNet models a bit more, and use more, data augmentation and possibly a different data set to work on these models to achieve a better performance. And yeah, thank you very much, and goodbye.